we're very glad to host Paula Harder today for the Lead Journal Club. Um, I think she has multiple affiliations and wears many hats, and I think she used the phrase "research nomad" to describe herself. So I think what's in a title as for the or what's in an affiliation. But she's going to talk to us today about physics constrained deep learning for downscaling and emulation. And the floor is yours, Paula.
Yeah, thank you so much. Thanks, Jayden, for the intro, and thanks for the invitation and for being here today. So yeah, just quick introduction. I'm Paula. I'm currently a PhD candidate. I'm just wrapping up my thesis, so fingers crossed. And I'm based, my main institute is Fraunhofer Institute in Germany, and the University of Kaiserslautern, which has been renamed to something more complicated. And then this work here, I'll be talking about two main projects of my PhD. And one project was done in collaboration with the University of Oxford, and one with Mila here at Montreal, where I'm also today, and IBM. So thanks to them. And yeah, so as Jayden already said, I'm going to be talking about physics constrained deep learning. One first part is going to be the downscaling part, and then about aerosol emulation. So why did I do the work I did during my PhD? So it would be very helpful for to have faster climate modeling. For one thing, if you're faster, you can increase your spatial resolution, or also just predict farther ahead, which could be helpful. It gives us more information about what to expect in terms of climate. And then also, if you just are fine with the resolution or the time frame you have, you can still save some computational costs, get results faster, or nowadays a lot of people talk about democratizing climate modeling. Ideally you can just run some climate simulation on your local computer. And then you all have the background, I think, for it. So there's two very common ways to use machine learning in that way to accelerate climate modeling. So one is for downscaling, increasing some already existing data's resolution. Either model can be also observational data as a post-processing tool to save run a model, for example, lower resolution, and then increase the resolution afterwards. And the other one is already during the modeling part to just replace some expensive modeling parts, also called surrogate modeling. In our case, we just took an expensive Aerosol microphysics model and replaced it with some cheaper ML model. One thing I ran into at the beginning, or at the beginning of my PhD, was, okay, I have this new network. It outputs sometimes negative masses. It doesn't conserve the aerosol masses that the original physical model conserves. And we can't integrate that into a climate simulation, which then motivated me to look more into how to incorporate some simple physical constraints into deep learning architectures. It's not the physics informed work you probably know, having a PDE as a loss function, and then that solves the whole PDE. It's more about positivity, some mass conservation. So like I said, first topic, constrained deep learning for downscaling, and then the constrained deep learning for aerosol emulation. So the first topic, the downscaling work, I just want to thank all my co-authors from IBM and Mila that helped me with that project. And you probably heard about both things. So machine learning, we have the field of super resolution, and it's sometimes a little confusing because you talk about upsampling when increasing the resolution and downsampling when decreasing. Whereas on climate science, it's downscaling for increasing and upscaling for decreasing. I probably mostly use climate science terminology today. And then, yeah, usually, of course, in machine learning, you more common to look at standard images, and then we have physical quantities for the statistical downscaling. There are also a couple different setups for the statistical downscaling, but we now just look at the equivalent of the super resolution one. Yeah, and what happens, I think, with most areas is the new methods within ML for super resolution, and then with a bit of lag, they are applied in climate science, and that usually works very well. So yeah, we just have some low resolution input, and yeah, we want to increase the resolution. That's the same we do in super resolution, and we can apply CNN, GAN, now maybe diffusion-based models to do that. But then what often doesn't work well is to obey some laws of physics. For example, if we just want to very simple have that the lowest water mass is conserved in the output, we have the same water mass still, but at finer resolution. That's not learned by the neural network. So we want to look into how to enforce something like that. And the way we do that is, yeah, there's several things to look at. So let's look at this, tiny example. So we look at atmospheric water mass, for example, and we just look at increasing the resolution by a factor of 2. It doesn't matter; it can be any factor, but here, for simplicity, let's consider that. So we have just focus on one input pixel. Of course, we have multiple. And in this input pixel, we know, okay, is this area, we have this water per area. And then in the corresponding superpixel, so the number of pixels that are in the same area as the lowest one, we have some predicted water mass. And what we want is very simply that the average, so the overall water mass per area, matches the one in the lowest one. So that would just be the average over the predicted pixels yi, matches the input pixel xj. And j just goes over all the pixels in our input. For the future, x is always going to be the input, y the output. So I think a very common idea is to, the first thing that people think about, okay, we can add that as a loss term, as an additional regularization term. So we, for example, we just have a standard MSE loss, and then we would just add a constraint violation term with some factor, and the constraint violation would just be some distance metric between what we want this to match x, j. So for example, the MSE, and then we need the mean, of course, over all the input pixels xj. So we have this constraint violation term for each input pixel, but here just showing for one pixel as an example, and then minimizing our loss also penalizes the constraint violation. But we found some problem with that can occur. So we don't then, running on our test set, we don't have any guarantee that our constraints are actually not violated. Also, the optimizing of alpha for our case was was very sensitive. If alpha is too large, we get no constraints violation, but a bad solution, basically just a blow up of the low res, because that conserves the mass too. And we then observed like a trade-off. Okay, either we get good MSE or good predictive performance, or we get good mass conservation. And then that's what motivated us to look in what we call hard constraining. And the idea is here, okay, we have our input, goes into our neural network, and we have our final output, and we want to put something at the end that enforces some constraint like this to like guaranteed. Also here importantly, this constraining layer is there during training. It's not like after we don't train and then put it in there after. It's there during training, even though we see that it doesn't have tunable parameters. But yeah, it's important to have that there during training both, and then of course also during inference. So one thing which I think was one obvious choice was what we call an additive constraint. We have our input pixel x, that should be xj, and then we get an intermediate output prediction, which we then readjust. And the readjustment we do so by construction. We have this mean constraint again. So if you would input the yi there, that would the sum would just cancel out and we would end up with xj. So yeah, but by construction we then have the conservation property we want to have for our final predicted superpixel. Not the intermediate one doesn't satisfy, but the final one. And we do calculate our loss on the final one. So that is taken into account. So we basically, make the function space we're searching for a solution. We make it smaller to only the feasible solutions. We can do the same with like a multiplicative readjustment, where again by construction the sum would or the mean would cancel out, and we would have the mean over the yi's would be xj. And yeah, then we also looked at like it's basically like this a softmax layer, but with a scale with xj. So this would also ensure that our output would be positive. But the exponential could be any other positive function. And then if we think in terms of predicting water mass, of course we want to have positive values only. A little more general formulation, but still only specific linear constraints. So we can have some function gi here to change the yi's a bit, and we could also apply some function on the other side. So this is our case we looked at. And then, for example, with this more general formulation, it would be straightforward to do the additive constraint layer, the multiplicative, and the softmax one, just slight adjustments. But for example, what we could look at is a weighted mean if we want to have that. For example, if we think about climate data, maybe not all the grid boxes have the same area, so we would have some longitude latitude weighting, and then it just a slight adjustment, and we could still enforce that. Also, what is possible as well, if we don't want to have a constraint per subpixel, but just one for the whole predicted area, for some reason we want this kind of global constraint, we can just change that we constrain on the mean over the low res. So we would take the mean over the low res and then make sure that the mean over the high res matches that. Also, we see later more about that. If we look at emulation for aerosol microphysics, the model we look at, we have what we do there is we have aerosol masses time t in a grid box in a climate model and predict them one time step later. And the microphysics model conserves the mass of one specific species. For example, that's aerosols. The overall dust mass, there's no emissions and things, so it stays the same in that model. And then we want to enforce that in our neural network, and that could also work with the same formalization. We could either do the additive, the multiplicative, even though here you have to watch or add some epsilon so it's not zero, or do the softmax with the exponential again. Yes. Let's see how we tested those ideas with some data. So I talked about water mass. So one thing we did, we just took ERA 5 reanalysis data, looked at the water content, mostly because it's a fairly easy thing to tackle. And the important here is that the low-res is synthetic. So we just decreased the resolution ourselves, but that just made it easy to create different data sets with different upsampling factors ranging from 2 to 16, and then also looking at spatial temporal downscaling tasks. But then we are also interested in how it performs for actually 2 different simulations. So if we run a model at low resolution and then try to get to the same model at higher resolution, where then of course there's some bias in there, but yeah, this is the WRF data set. And yeah, so for the ERA 5, we had those 3 types of data set. One where you just have one input and one target, then time series of 3 input data, which we then super resolve into a time series again spatially, and use the information of the previous time steps, but then also do spatial temporal super resolution, or time frame interpolation as it's sometimes called, where we increase also the temporal resolution, just to see have different cases of downscaling and see if our constraints are applicable across all of them. And then what I mentioned before, we played around with different upsampling factors, so 2 times, where you can see we always have the same high res, and then we create the low res ourselves, 4 times, 8 times, and 16 times. Also again to see if the constraints are work across independently of the upsampling factors. And then the WRF data, that was some data set IBM had, like this operational weather forecast, actually, on a smaller area, Lake George in New York. And yeah, that's 2 different simulations, one at 3 kilometer resolution and one at 9 kilometer resolution. Here it's important to keep in mind that when we decrease the high res resolution, and it's not a perfect match with the low res one, but someone is not muted, but yeah. No problem. So yeah, but there's some there's some differences there. And then the types of experiments we did, we wanted to look at a variety of architectures. There's the standard CNN that is, I think, still the most common choice for downscaling tasks. Of course, GANs become more popular. Then for the temporal stuff, some mixture with recurrent neural networks. And then also we have newer work with where we used for neural operators to have a kind of upscaling factor independent downscaling. But the message there was again to see just that the constraints work independently of the architectures. So we didn't find big differences. So I think you could basically add any architecture here. Let's go through the results for a bit. And so this is just some visual results. So we have the low-res input, the unconstrained CNN, and then we actually see that with applying soft constraints, we get some artifacts that are, we have them in the unconstrained one, but they get way worse. And then for all the different, those are 3 different hard constraining methods, we can see that actually those stripes, especially in this one and that one, disappear, and it's very close to the high res. So that's just an example where it's the visuals get improved by the constraining. So there should be a, okay, at a loss curve, but I don't know, maybe it comes later. And then we looked at, we looked at some metrics. For example, the root mean squared error. We compared like a CNN without constraints, with the soft constraints, and then with different constraining layers. And then also, we looked at how much is the mass conservation actually violated, and also how many negative pixels we have. So we can see that the root mean squared error gets significantly lower by applying hard constraints, which is nice to see, and also a bit surprising, because the main goal is to have this mass violation to 0, which it does. But then as a side effect, because I guess we're making the learning task easier, we also get better root mean squared error. Whereas the soft constraining, it makes the root mean squared error worse, and it decreases the mass violation. So like I said, we have a kind of trade-off there. Also increases the amount of negative pixels by a large amount. Here's the loss curve. So on the left, we have the training and the validation loss. What is important here to see, so the blue one is, so it's two same architectures, one just with the added constraint layer, that's the blue one. The red one is just standard CNN, no constraints. And what we can see, that the loss curve for the standard CNN is pretty spiky. And the loss is way smoother if we apply our constraint, and it also converges to a lower local minimum. So that was interesting to see too, and same for the validation loss. Here, if we look at different upsampling factors, again, the first row is the input, then we have our unconstrained prediction, and then we have the softmax constraint prediction, and then we have our target, and the columns are different upsampling factors, so the task gets harder as we move to the right. And we can see with 16, it just doesn't perform well, and the constraints also don't help that much anymore. But for example, if we look at 8 times, we can see that the unconstrained one struggles to get this diagonal structure, where with the constrained one, we can replicate it nicely. And also this, again, reflects in the root mean squared error, and also other scores. We looked at that the hard constraining one actually improves the predictive performance. The GAN looks similar, again, different metrics, root mean squared error, mean average error, structural similarity index get a bit better when constraining the GAN. And then also here, this is the spatial temporal super resolution, where we observed the same and had even a stronger effect. And then, we looked at the WRF data, which I said before. So we have the low res, which is a different simulation than the high res, so no artificial low res here. And we can see that the unconstrained CNN is kind of blurry, whereas the constrained one, reconstructs more of the fine details, which was interesting, a bit surprising also to see. But it basically, I think, again, the constraining helped help the CNN to train. And we get a slight, it's not that big, the improvement measured in the scores, but we do get an improvement there as well. So now I talk about the other topic. There's some overlaps where we replace a cost-intensive aerosol microphysics model with a neural network. And again, thanks to my co-authors that helped me a lot with that. And what we did here, so there's this within global climate model, there's some modeling of the aerosols, and within the aerosol model, there's this aerosol microphysics model that basically, just roughly what it does is it models the size distribution of aerosols for different aerosol types like sulfates, carbons, dust, sea salt, and because the size then later determines things like radiative properties or cloud properties. So that's important to model, but it's cost intensive. So the idea was to replace this microphysics model M7 with a faster neural network. Yeah, the way we went here, or as the standard way for an emulation task like that, we just took some climate data and generated lots and lots of input-output pairs of this original model, couple million points. What we did first here was actually like we just had 4 days throughout the year, and 2 days were taken for training, 1 for validation, and 1 for testing. Later, now I actually updated the data set to have multiple, like 2 years for training and all different seasons, and then next year for validation and then for testing, because yeah, there's some seasonal differences which then are tricky if you don't have that in your training data set. But here are the results for the older data set. So it's simple and fairly small architecture, also to then actually be faster. That's a trade-off too. The inputs are some atmospheric variables such as temperature, relative humidity, and then the aerosol and aerosol masses and numbers at time t, and then we output the change in aerosol masses and numbers and also the water content. The way we constrain here is a bit different. So we have this set of different aerosols, sulfides, dust, organic and black carbon. And for each of these species, the way the microphysics model work is that the masses stay the same. So if we predict change, we want that for one species, the changes add up to 0. So overall, the overall dust mass within one box stays the same. And again here, you can either add this as a loss term, so we want the sum to get close to 0, so we just penalize that. Or you could do something called completion, or you just choose one variable or select it randomly and set it as minus the sum of the other variables of that species. So by construction, they add up to 0 again. This can be done either offline and online means. You can do it already while training or after. And here it didn't make a huge difference for us to include it or not include it during training. So for the positivity, it's fairly easy. It could be even easier, but because we predict the change, not the full value, we need to add it up to the input again and then enforce that to be positive. So you can add a loss term with a relu, but have to add the input x to the output y, or also add a relu layer with the sum. So by construction, this is minus x if the sum is negative, and it just stays y if y plus x is positive. The tricky thing here is actually not on here, is that you scale y's and x and you scale them differently, and because of the aerosol properties, you have crazy numbers during the scaling, and for numerical reasons, doing back and forth scaling for the constraining actually can mess things up, but it's very technical. So let's go through the results here and let me have a look at the time. Okay, so again here, the loss curve, here we see the loss curve for the soft constraints ones, that the MSE is not really impacted, nor is the R² value. But if we look at the mass violation, we can see here that if we include the mass loss, it gets slightly, smaller than without the mass loss, but yeah, it's not significant. And if we include this positivity, this ReLU term, we actually get more mass violation in spike hair loss. And the negative fraction, so that the fraction of predictions that result into negative masses, which is actually quite significant. It's very spiky during training, and with the positivity loss, we can decrease it, but only to a certain amount, and it's still very unstable and hard to train. Let's look at the results. First, we just focus on the mass conservation. So what we see here, we just have a basic neural network without any constraints. Then we include the soft constraint, and then we include the hard constraint. And we can see here again that the soft constraint does decrease the mass violation roughly by like 3 times, but it also decreases the accuracy of our prediction. And same though for the hard constraint, but there at least we get a complete satisfaction of the mass conservation. If we look at the positivity, so here again we have the basic neural network, then the soft constraint and the hard constraint one, and we can see that with the soft constraint we decrease the negative fraction a bit, but there's still 9% negative values, which is of course a problem for plugging it back into a climate model. And then also a significant decrease in the score. So here we actually see here hard constraints is correction with the ReLU layer, and the sum actually doesn't harm the performance and helps us to get 0 negative values. Not to forget about that, the point we're doing is to actually be faster than the original. So here we have the time the original needs to do a global prediction for all the grid boxes, every pressure level. And then we test the neural network just purely on a GPU, assuming this is the assumption we do have our data on a GPU, and can just do a prediction there. For example, if for some reason we have a GPU climate model, and then we would be 11,000 times faster, but that's also I think a bit of apples and pears comparison. But then if we move to the case where we move the data from the CPU to the GPU, the input, perform our prediction, move it back to the CPU, which is a little more realistic. Where you could have your climate model on the CPU and then do the transforming and still run your network on a GPU. Some bridge, but then you would achieve 60 times speed up. And for the just CPU only case, one single CPU, there would be a 2.8 speed up. So that shows. I mean, with multiple CPUs, there is maybe also some improvement that can be done, but basically here looks like the strength is mostly speed up on GPU. Also, if you can make your neural network smaller, that will also speed things up. So now we did integrate it back into ICANN. Actually, if anyone is ever working on that, which I found good to work with, is the Fortran-Keras bridge. So the way it works, it takes a trained model from Keras output file, like the weights file, transforms this weight file into a TXT file, and then has the layers, like simple layers already pre-implemented in Fortran, and then you can just load your TXT file in the Fortran code and use the pre-implemented layers to run inference. There's no training, but the way I used it, but you can run inference easily within Fortran. I worked on Python only, so I had to transform it from Python to Keras. But yeah, that's also fairly easy to do. And then just replacing the function called M7 function with the neural networks version. That was actually turned out was pretty was harder than thought. So one thing that I noticed there was that if we have out of the distribution samples for a neural network within our simulation, it crashed pretty quickly. So that's why we changed the data set from more diverse data from different seasons, different times of the days, all levels, all areas across the world, which was very important. And now it's running stable for the first time, but still just some first results now. And here it actually helped to make it a little bigger, the neural network. I decreased the size to be faster, but yeah, it's a trade-off. If it's too small, it's just not doing well. And then here's some first online results where the dust burden over after a month, and we can see some drift here. We're a little too much mass, but yeah, that's without constraints. So hopefully, that the constraints will help with that. So that already brings me to the takeaway here. So if you ever work with the deep learning neural networks and you have some simple simple constraints, you want to be sure that they are not violated by your neural network. You can do that. It's very easy, such as conservation of mass, and even in some cases it can help the performance, and sometimes it's a trade-off, and sometimes it actually boosts the performance, because I assume it helps the learning task, makes it easier. And then with soft constraints, I think in my experience, this was always a trade-off between accuracy and constraint satisfaction, but there might be some cases where they're helpful. But here in our cases, the hard constraints were performed better, had the guaranteed satisfaction of constraints, plus they were actually easier to handle and to train. So that was a clear win, but I also know that there's some cases where it's not that. And there's some, for example, the hard constraints, we only incorporated fairly simple constraints, where with the soft one, you can put anything in your loss function. So that's a big advantage of the soft constraints. So the work in progress and the outlook and potential next steps here is, in terms of constraint methodologies, it would be, of course, interesting to not only have those simple linear constraints, but look into non-linear constraints. Here, my work was mostly motivated with constraints that actually came up in the application cases, and there weren't really any non-linear constraints. So I think, I would be interested to have an application case where there are some non-linear constraints that need to be satisfied, and then also question how to incorporate them. And then I looked a bit into improving actually the soft constraints, because I think there's some potential, for example, doing some scheduling, so just increasing the factor that how much the constraints are weighed during training, maybe, so it first finds an accurate solution, and then within that closer space it finds one that is more physically plausible. And then also what I showed last with the correction and completion methods, can actually combine that to then have both a hard constraint to have soft and mass conservation and positivity. For the downscaling one, I think it would be interesting to look at newer architectures and transformers, normalizing flows, or diffusion-based models, and then also here we looked at cases where there wasn't a strong bias in the low res or no bias because it was synthetic, but to have two-step approach where you remove the bias and then you do the increase in resolution. Yeah, and for the aerosol emulation, I had some different constraining methodologies, and now I'm applying them to the other problem, vice versa. And then also, integrate that, and I think, there's some potential for making the decreasing the parameters of the neural network emulator to then actually be faster again, and also maybe look into this on a GPU conversion of that something the emulator can shine more. And that's already it. So I think this is a QR code to one of the preprints. I'm happy for questions. Also feel free to write me an email if questions come up later. And that's it.
Thanks for the talk, Paula. This is incredible work. Wait, someone's okay. I think this is time for questions. Mostly folks online, I suppose, unless Joe and Kate, if you have a question. Feel free to just unmute yourself and ask Paula the question.
Are we unmuted?
I think we're unmuted, yeah.
Hi, Paula, can you hear me?
Yes, I can. Can't see you, I think, but I can hear you.
I had a question about like your first section of results, that table.
I wish there was a function to jump. Probably there is, but
Yeah, this one. Could you maybe like walk through how the soft constraint is doing so much worse in terms of mass violation than the unconstrained?
I'm sorry, is your name Samantha? Okay.
That's a really good question, and I can only, I think, describe what I what I observed, maybe not fully explain it. So you remember there was this term, this alpha, or like some factor in front of the soft constraint. So that needs to be tuned, and depending on how high this is, it would change this and this number. I don't have it in here, but I could decrease the mass violation, but then I would increase the error significantly. So here I choose one where I was like, okay, we decrease the mass still and don't get that much worse. But it's basically, it's very sensitive to the factor, and I can either, if I want to match the root mean squared error of the unconstrained one, I wouldn't really decrease the mass violation. Why that is the case, I'm not really sure. It's just something I observed, and I think that could get better with what I mentioned at the end, where I wouldn't have the constraint, and I train my model for a bit, and then I would just put it with a very low alpha, and then increase the alpha as I move on along training. So I try that now for the first time, and it works a bit better. So I guess it just ends up in the wrong area of the loss landscape, but I don't know exactly why. I mean, here for why the hard constraints are so much better, here it's by construction just guaranteed that the mass violation is zero. There's nothing, the neural network doesn't learn that or anything. It's just forced to only look at solutions that obey the mass constraints. So that's why, yeah, there's no skill basically for that. It's just something I tell, okay, and then, but within that space, I constrain it to, it actually finds a better solution because it's a smaller space, I guess. And here it is just confused by by the two things it needs to optimize. As maybe different optimizers. So here it's just a standard like atom optimizer. Yeah, I think there's the potential that yeah, if you put a lot of work in here, that could get better, but there's not really an advantage to the hard constraint. So I also didn't put in, yeah, I didn't put in that much work into the soft constraints because there was not really any promise to be better, or there is no possibility to be better than the hard constraints. I hope that answers your question a bit. Okay, I think there's another question.
Yeah, Sungrit, please unmute yourself and ask the question.
Hi, Paula. It's really interesting talk. I have some question about the second part, aerosol emulation. So you use FKB to implement the emulator to icon module, and you experience some instability like crashing. And yeah, I have done similar work for different parameterization using FKB. In our case, using the ensemble prediction help like stabilizing the online coupled simulation. So I wonder if you guys have tried ensemble prediction instead of using just one.
What prediction on one? I didn't understand.
So like when you couple the neural net emulator to icon, but in this case, I believe you use only one emulator, only one neural network. So instead, yeah, you can couple like multiple and averaging and yeah, send it back to the GCM, I mean icon.
Okay, yeah, I thought I did a bit of that. So I have 30 output variables. So I split it up into dust, which has 4 output variables, carbon. So I did it a bit, not a single. So you mean a single network for single output variable, or?
No, you just take up the server of your neural network emulator. So you can I believe you have like several emulators, right? Like the best emulator, second best emulator, third best emulator after you training. You use all of them. You use all of them, and then yeah, you're averaging the result from
Sorry, I completely missed it. Okay, so like do an ensemble and then do more. Okay, that's
that helped. Yeah, that helped stabilizing. So maybe I'm curious. Yeah, it will help in this case too.
Yeah, no, that's great. I'm very happy to try it out because it's it actually is, I've been trying a lot of things to make it be stable. I mean, one thing is that then it decreases or it makes it slower again, right? Because you need to run all the different models. So it's a trade-off, but I think for stability, that also, I mean, it makes sense. It's a good idea, and yeah, better a stable slow run than no run at all. So,
right.
And ideally, you just parallelize. Yeah, you can parallelize the different ensemble members, kind of the different neural networks. Okay, yeah, that's super interesting. Thanks for the comment.
No problem. Good luck.
Thanks. Yes, open. Oh,
hey Paula, great talk. I was wondering, so you alluded to this in your next steps. Are you going to try the softmax for the aerosol microphysics scheme? And actually, my question about this is, does mixing of different species into different like aerosol classes, is that going to pose an issue with that? I'm not familiar with your microphysics scheme, but you had a diagram of that.
Yeah, so I tried out. So the problem a bit with the softmax constraint, I'm going a bit into technical details, but it does perform the best when the data is scaled between 0 and 1. Even though my aerosol emulator performs much better on like a set scale, so minus mean by standard deviation, just of the distribution it has. So the softmax layer didn't work in my first tries, didn't work that well, but it would be helpful to have, because and I mean, the one argument for the softmax one was also the positivity, but then here it's tricky again because I predicted changes, which can be both positive and negative. So if I would predict the full mass value at the next time step, I think that would work. But for the tendencies, it's a bit tricky. So far the like the other methods, like the additive one or just the other multiplicative one, perform better than the softmax. But I'm not sure what you meant with the different aerosol species or classes.
Oh, yeah, I guess that was the second part of the question. Do you, I think you had the diagram of the scheme on your slide somewhere.
Yeah,
And it could just be that I didn't understand it, but it showed some mixing of the same species across different modes. And I'm just wondering, I don't know, I'm trying to think of this as an analogous thing to mixing of atoms across molecules in my gas phase work. And I'm just not sure if that's an easy mixing problem where it's that requires more sophisticated mass conservation or not. I don't know.
So
like if you scale sulfate in one mode, or if you scale an entire mode.
I would scale across. So okay, no, I mean I scale each variable, and it's like in terms of normalization, every variable is scaled separately, of course, because they all spin very different orders of they have all very different scales. But then you mean, when I constrain, I would constrain per species. So the way this model works is that even though there's some mixing, so the overall like carbon mass is the same.
Yeah, gotcha. I see.
But I think I actually have to understand better what you meant.
It wasn't a very well posed question. I'd have to think about it more too. Thanks.
I think we have time for Pierre. Perfect.
Yeah, as usual. Thanks so much, Paula. Yeah, that was great. I just put a paper in the chat, but I realized that you actually said it also, that paper, from Tom Beukler, where we try to impose hard constraints within neural networks. So you might,
Oh no, I think I sometimes I don't have enough references on my slides.
No, that's okay. That's okay. Just
it actually it did inspire some of my I think it's the paper I know, because you have a couple, but it was definitely helpful. Yeah, thanks.
And if I may, I had a question. I really like the way also like you compared like the different architectures, and also assessing why the weak regularization. And that was our experience as well, that it doesn't work so well because there are parts of the flow where it works, where some parts where it doesn't, so it's like, that's, you would almost want the alpha to be adaptive, to some extent, but whatever. But I was curious, because I'm always thinking in terms of downscaling, that there's super resolution in a computer vision sense, right? You can make up stuff, right? Because you've seen a lot of faces, etc. But there's also the fact that the landscape is the landscape, right? The landscape doesn't move, right? I mean, they are like features that are always kind of baked into that, you know. And I'm curious, like, have you tried different things? What's the impact of, and then, for instance, like conditional strategies, but then it becomes very tricky because it becomes very high dimensional as opposed to regular super resolution. You know, like for instance, you have a river somewhere and then you have topography here, right? It
Yeah,
makes it
I think-
annoying.
No, I think that's definitely, I should have put that in the future. I think that definitely it would definitely make sense in our model to include the topography, because I think it would just boost the performance of the super resolution significantly. It's just something, because we just mostly focus on, okay, how does the constraint affect the performance, and not how do we get the best possible performance overall. But I think in terms of improving the downscaling tests, including topography, would make sense. And it actually, it's just something I didn't manage to do time-wise, but I think it shouldn't interfere with constraints or anything at all. It's just a different input, and having multiple inputs or even multiple outputs actually shouldn't change anything. It's just a bit more work.
Right. Thanks so much. Yeah. Thanks for joining.
So yeah, as Paula said, if you have any further questions, you should email her. But I think we should thank her again for this awesome talk and taking the time.